So solving sparse linear systems. So what's the challenge? So the challenge is, how many people know what does MATLAB actually do when you do A\B? LU decomposition, what did you say? QR decomposition. Any other questions? Any other answers? I can have like 8 or 7 other answers and you can all be correct. Because what MATLAB does is it's actually very smart in interrogating what is the matrix A and choose different solvers for different A's. So for example, if A is symmetric and it does something else, it at least tries to do something else. If A has a banded structure, so basically all the sparse system we looked at is banded, so that means there is a band outside of which are zero. So we have tridiagonal or pentadiagonal, whatever diagonal, it's going to be banded, right? So MATLAB does even something else. So you have a array of schemes to solve it, but whenever you do \, MATLAB is going to use what's called a direct solver to solve it. So the direct solver is like, if you take a matrix A, if you do LU decomposition, that's I'm decomposing A into L times U. If you're doing QR decomposition, I'm doing A equal to Q times R. I mean, there are different decompositions. In the LU decomposition, L is going to be a lower diagonal matrix. It's 0 up there and non-zero only on the lower diagonal part. U is upper diagonal. It's non-zero over here and 0 on the lower diagonal. So QR decomposition is different. R is also upper diagonal. I don't know like why they use different names for U and R, but like they are exactly the same meaning, right? Upper diagonal matrix. And the Q is something different. It's called the orthogonal matrix, orthonormal matrix. So Q has the property of Q transpose Q is equal to Q transpose is equal to identity. So that's there are different decompositions, but all of them have the purpose of making the inversion of each part of the decomposition very, very easy. Why is that the case? Yes? No, L times U. A equal to L plus U would be too easy and it doesn't help. Right? So why does the decomposition help? Is because each component is very easy to invert. So for example, if I can say A is equal to L times U, and L and U are both easy to invert, then solving AX equal to B is becoming the composition of two easy problems. So first, because AX equal to B is basically L times U times X equal to B. So if I want to solve that problem, I can first solve L times Y equal to B. Because L is easy to invert, this is easy to solve, right? And once I have that Y, I can solve another problem, U times X equal to Y. By just doing these two problems sequentially, I basically solved A times X equal to B, right? This applies to any decomposition. There are complex decompositions where you can decompose A into the product of 4 matrices. Don't remember what they are. Like they have like a permutation matrix on left and the permutation matrix on the right, and then after the permutation you can decompose it. But basically, as long as each individual element in that decomposition is easy to invert or easy to solve, not like invert is just a word, is a verb of describing solving linear systems, right? As long as each matrix is easy to solve its associated linear system, solving the AX equal to B is just a step-by-step task. So for example, if you do LU decomposition, L and U are easy to invert because L, for example, lower diagonal, how do you invert it? Just think of the first row. The first row is just a single number in the matrix, the one element. times the first element in the vector x equal to the first element of p. It's a scalar equation, right? The first row is just too easy to solve. Then once you have the first element, just go to the second row. The second row is the first element in the row of the matrix times the already known first element of the vector plus the 2 entry times the unknown. So it becomes another equation with only one unknown, right? Because the first unknown is already solved. So this is called the forward elimination. Basically, you eliminate the unknowns just one by one. If you have an upper diagonal matrix, the procedure reverses. It's called the backward elimination because you start with the very last entry of the matrix. It's the same, right? If you look at this upper diagonal system, if you just flip over all the entries in X and flip over all the entries in Y, you get a lower diagonal system, right? So it's equally easy to solve. That's why the LU decomposition has to be L times U. If you decompose into L plus U, yes, then you have to use the iterative methods to solve it, right? That's what we'll be talking about. Okay, or if you do QR, R is easy to invert, and Q, because of this property, the inverse of Q is Q transpose. That's even easier, right? So these kind of methods are what MATLAB does if you do backslash. MATLAB will not use Gauss L if you do backslash. All right. Okay, so what's the problem about this method? One word, it's called fill. What does fill mean? Fill means when you decompose a very sparse matrix into the product of multiple matrices, you end up filling the zero entries of the original matrix A. For example, if you do LU decomposition, so QR decomposition is the most hopeless. It'll pretty much fill everything. If you do LU decomposition, the L and U will end up being a banded matrix. So the bandwidth of L and U is pretty much the same as A. It will not fill these zero entries, but it'll fill everything in between. So that's actually that's actually not a problem if we have a matrix of this kind, right? So if we have a matrix of this kind, actually backslash would be perfect because MATLAB is going to look at it, find it's a banded matrix, and no problem, I will use LU decomposition. Because LU decomposition is not going to fill here and here, right? It'll fill these entries. It'll fill these kind of zero entries, but not the majority of the zeros. So for one-dimensional problem, backslash, you don't even have to look at iterative methods. The problem becomes severe, becomes a little bit of trouble in two-dimensional structured problems. So over there, iterative methods and direct methods are kind of problem dependent, which one is better. And iterative methods really wins when you have a three-dimensional problem, no matter structured or unstructured. And direct methods has no hope if you have an unstructured problem. Unstructured means the matrix would be complete. I mean, you can't predict where these non-zeros are. So the first element, the first row may have a non-zero here, the second element may have a non-zero here, and if you use direct methods, very soon your entire L and U will be completely full. So you get a completely, every single entry is going to be, I shouldn't say every single entry because you still get a few non-zeros in the beginning, but like 99% of the elements will be full, will be non-zero. So you can imagine, if that is the case, extraordinary amount of work needs to go into factorizing and solving these systems, right? For example, just to think of how much work needs to do a forward elimination. You start with one single number, then you proceed with two numbers, then you proceed with three numbers, right? The more downward you go, if the system is fully dense, the more work you have to do. So it's basically kind of the elementary math problem of plus all the way equal to n. That's approximately equal to n squared over 2, right? Approximately. So the amount of work you have to do goes proportional to the square of how many non-zeros you're gonna have. So that's not very good. And that's still not the majority of the work. The majority of the work is actually doing this decomposition. Doing this decomposition usually scales with n to the cube. The factor is usually smaller than half, but like still, when n is large, n to the cube is like killing. So yeah, you can simply do an estimate of okay, so if I have a problem of 1,000 unknowns, this is still in the acceptable range of what can be done using computers today, right? Billing operations, no problem. N is equal to 1,000,000. You need to think about it. Maybe if you have a class of computers, you can still solve it within reasonable time. If n is 1 billion, good luck. Maybe you can get it before you retire or something.